I would like to give some pointers about good practices in fluorescence. This is hopefully something that will now make more sense to you since you have some experience in the lab. Some of you have seen the consequences of having concentrations that are too high in the fluorometer. You get saturation of the detector and you don't see a linear response. You have seen that sometimes you get strange results in TC-SPC, and this can happen perhaps if the signal is very low so that the number of photons is simply not representative of the sample. Not sure what all the reasons could be, but as you have seen, if we try a slightly higher concentration in the TC-SPC, we can also get very good results and reproducible results. This is an overview of some good practices. Sample preparation should involve making sure that the sample is free from particulates or anything that scatters. This has not been such a concern for us, but it is oftentimes a concern if you're looking at proteins or polymers or more complicated samples. The sample concentration must be optimized to achieve maximum possible signal with minimum inner filter effect. The signal should be optimized by determination of an excitation spectrum to determine the maximum signal for the emission experiment. Spectra should be corrected for variations in the light source, the spectrometer throughput, and detector response. These things are actually done automatically for you by the software in the fluorometer. And regarding the excitation, I, for consistency's sake, chose 509 nanometers in the fluorometer. Maybe that's not the best choice in the long run for all the data, although it certainly works. It is an important measurement since it tells you where to set the emission monochromator in TC-SPC to ensure that you get the most signal. There are other options for excitation. If, for example, one wants to get a really nice line shape in emission, probably the excitation should be moved back to lower wavelength, that is higher energy, since the lambda max of fluorescein is around 490. We have no choice when it comes to the excitation laser. Typically, these kinds of lasers are at fixed wavelengths that are determined by material properties. The fluorescence measurement assumes that the light can get in and out of the sample, and this slide shows you the effect of absorbing samples on the ability of light to do that. If the sample is too absorbent, there's a so-called inner filter effect. It filters out the wavelengths of the light so they don't excite as many molecules, and then it filters out the light that's emitted so that not as much of the light gets out of the sample. And you can see that in these cuvettes here, and of course, that depends on the absorbance. Let's discuss the absorbance. Here you see a plot of the decrease in radiation intensity, that is to say, the decrease in transmittance as a function of the path length, and the absorbance. The transmittance is 10 to the minus A absorbance. So if the absorbance is 1, the transmittance is 10 to the minus 1 at a 1 centimeter path length. That is to say that only 10% of the light gets through the sample. And here you can see on a quick plot, that if the absorbance is higher than 1, it quickly drops to such low values that it's pointless to try to do absorbance or fluorescence. We want to be in a range where most of the light is getting in and out of the sample. And that is why we say that the absorbance should be 0.1. Keep in mind that that's kind of the minimum criterion for an inner filter effect. Then we found that we had to dilute the sample even more in the fluorometer. The reason for that is not because of the inner filter effect, which is already pretty well taken care of at 0.1 absorbance, but rather because so much light is leaving the sample and hitting the detector that the detector is saturated. And when the detector is saturated, it doesn't necessarily send you a warning. It just gives you a spectrum that's not really the right spectrum. The way to determine that you're in the linear range is to decrease the concentration by a factor of 2, and then hopefully you would observe that the fluorescence decreases by a factor of 2. Or you could decrease it by a factor of 5 and see that the fluorescence decreases by a factor of 5. Often when I see that it's saturated, I will decrease by more than 2 because you could spend a long time if you just go in factors of 2. I think some of you have seen that you must go to a dilution factor of 100. So that would mean quite a number of dilutions by a factor of 2. At the beginning, I mentioned light scattering. Light scattering increases as the fourth power of frequency. So that means that as you have increased absorbance in the blue or excitation in the blue, you have an increased scattering background. That background is not observed directly in fluorescence, but it can be seen in the absorption spectrum, usually as a rising background that's rather steeply increasing, again because of this fourth power of frequency. However, the scattering will cause a distortion of the fluorescence spectrum. And so when you see scattering in the absorption spectrum, you should filter the sample or take other measures to ensure that scattering is not distorting the signal. Impurity scattering is typically what we call Rayleigh scattering, scattering by particles that are quite a bit smaller than the wavelength of light. The Rayleigh scattering cross-section depends on the sixth power of the particle diameter. Again, this simple model breaks down when the particle diameter approaches the wavelength of light, and then you get into the range of Tyndall scattering. You see here that the scattering is inversely proportional to the fourth power of wavelength, which of course means that it's directly proportional to the fourth power of frequency. And it has a dependence on the index of refraction because of local field effect around the particle. Typical particle sizes that cause problems are somewhere between 10 and 100 nanometers. These can be nanoparticles, hairs, polymers, proteins, aggregates, or any kind of impurity that is in that size range. For this reason, a 20 nanometer filter is usually used, the type that fits on the end of a little syringe, to clean up the sample. We have not encountered photobleaching, as far as I know, in the course of our experiment. However, photobleaching is a real concern, and uranine, which is actually fluorescein, is a classic case of the importance of understanding photobleaching. Fluorescein was one of the first fluorophores used. It has a very high fluorescence quantum yield. It's excited in a good region for typical lasers. It was used in confocal fluorescence microscopy. And you see here an image that shows what happens when a sample is irradiated for a long period of time. Actually, what a long period of time is depends on the intensity of the radiation. If you're using a focused laser, that can be a matter of minutes, sometimes even tens of seconds. So it's important to develop molecules that have more robust fluorescence quantum yields that are not affected by the kind of non-radiative processes that cause decomposition, which is probably what's leading to photobleaching. We've talked about quantum yield, but we have to be careful to distinguish between absolute quantum yields and relative quantum yields. In our measurements, we're always measuring relative quantum yields. That is to say, the quantum yield of the molecule and quencher relative to the quantum yield of the molecule without the quencher. What is the quantum yield of the molecule without the quencher? Well, to measure that, you would actually need to use a device known as an integrating sphere, which accounts for the incoming radiation intensity and measures all the photons that are being isotropically emitted by the sample. This requires a spherical geometry. An integrating sphere is not a common piece of equipment in most laboratories, and we rely on the literature. So I will ask you to look in the literature for a value for the fluorescence quantum yield of fluorescein or uranine, which is the same molecule, keeping in mind that it might be a little bit different in different buffers. Can buffers themselves act as quenchers? Indeed, they can. In fact, this is one of the reasons why I was interested to compare phosphate, borate, and phosphate at different pH. Let's talk about how to determine the relative quantum yield if we know the absolute quantum yield of a molecule. The relative quantum yield between phi and phi r depends on the intensity of the fluorescence coming out, I over IR, but also the absorbance of the samples and inversely relative to the emission. You would like the absorbance to be as similar as possible, and so usually you try to find an excitation wavelength where that's the case, but it's not always possible, and so this is the correction that you would apply. Because if one molecule absorbs more than another, it will be promoted to the excited state more efficiently. Finally, if the solvents are different, then you have to use the index of refraction squared ratio here. But of course, usually the solvents are the same, and so this correction does not apply. This simple formula allows you to calculate a quantum yield from a known standard. Phi r are the tabulated absolute quantum yield standards shown on the next slide. These are tabulated absolute quantum yield standards. One of them is fluorescence, and you can see that its quantum yield is tabulated here as 0.95. You can find other values in the literature, and it may depend on solvent and some other consideration. You should do your own literature search. I didn't give a reference here, and so this is really not a value that you should rely upon. I'm sure that you'll find one in the literature. Quinine sulfate is listed even though it doesn't have a super high quantum yield. It was the first known fluorophore. Other famous fluorophores are rhodamine, for example. And there are different rhodamines. Actually, they're not listed here. They're both listed as rhodamine, but there's rhodamine 6G and rhodamine 123. And then it also may depend upon exactly where you excite them. Other common fluorophores includes the amino acids tyrosine and tryptophan, which are quite important. Even though tyrosine has a relatively low quantum yield, and even tryptophan is not super high, but because these are found in proteins, these can actually be used as standards for measuring quenching in proteins or rotation in proteins and other aspects of protein dynamics.